Hello everyone, welcome to Binpipe. Today we'll talk about something very interesting. We'll talk about how we use SSH to connect to servers and what is the public key encryption mechanism that goes behind the scenes. So the first thing is how servers communicate over SSH. That's what we are going to talk about. And then we'll go on to understand how encryption works, what encryption is, and how does it allow you to transmit your messages safely. And finally, we'll take a deep dive and understand the mathematics behind public key encryption. Now, there's a lot of math that goes behind this encryption. So those who are curious to know what is the exact mathematics, what are the formulas that goes to do the public key cryptography, so they can watch this video and understand what is going on under the hood. So first thing, how servers communicate, then we'll understand how encryption works, and then the mathematics. Well, so let's get started. Before we visit SSH, let's go back about 70 years ago to the 1960s, when communication used to happen only over something called Telnet. So Telnet was a protocol where you can transmit your information through the command line, and that is sent in plain text. So I'll go ahead and share a diagram with you that will explain how Telnet works, and that will set up the stage for us to understand how SSH works and how SSH is encrypted and how is it safer. So first of all, assume we have a server A and we have a server B, and we want to communicate from A to B, B to A, and so on. So if I send a message from A to B, I would be supposedly sending the message as a plain text message, and the same thing happens when B sends a message to A, and there is no authentication whatsoever. So if there is an eavesdropper in between, like someone who is listening to what A is saying to B or what B is saying to A, so this guy will read or get the plain text message and decipher it and understand what's the communication going on. So this is an unsecure way of communicating. So this is what was used with Telnet. So in Telnet, you have a Telnet client, which you can see here on the left hand side, and you have a Telnet server which runs a daemon called Telnet D. So when you send a message from the client to the server using the Telnet protocol, there is of course an authentication mechanism, but even the authentication username and the password is sent over plain text. So then what happens here is this eavesdropper guy can even know what username and password is, and later on use that to hack the server or go in and get some more information from there. So that is the problem with Telnet. It is good, fast, everything is fine, but this encryption is missing. Like well, I'll tell you what encryption is, but this sending message in a plain text means anyone listening to that can easily understand. So let me explain what encryption is now. So here you can see two figures, and say both of these guys are talking, and say the guy on the left is trying to say something to the guy on the right, and there are other people there listening to the conversation as well, but these two people have made some arrangements, like they send a message, but they know certain words do not mean literally what they mean. So they have an arrangement between them. For example, say the guy on the left wants to say something like send a dinosaur to your garden. So this is the message the guy on the left sends to guy on the right, and they have an agreement between them beforehand that dinosaur actually means gift, and garden actually means father. So they have exchanged the meanings of these words earlier, that this literally doesn't mean what it is, but we have a key here that only you and I know. So then the message is received by the guy on the right, and he flips it with the words from the map. So the message actually he gets is sent a gift to your father instead of sent a dinosaur to your garden. So what the other guys who are eavesdropping listen is send a dinosaur to your garden, and that doesn't make sense to them. But when the guy on the right decrypts the encrypted message using the key and the algorithm that these two people have agreed upon earlier, then it makes sense to him. So this kind of communication is called encryption, where you actually mask the meaning of certain words or certain parts of the messages and send it to the other person who knows the meaning because he has a key or a map. So the same thing happens with SSH. So in SSH you have a client and a server. The client initiates a SSH connection to the server, and then the server sends a random message to the client, and the client encrypts the message using the private key and sends it to the server. I'll tell you what a private key is in a while. Now you can take the previous example and just imagine private key is something like the arrangement made between these two, and it is some hidden information that helps you to encrypt and decrypt. And then the server decrypts the message using the public key it has, and if the message is same, then the client is granted access, or else the access is denied. And if it is granted access, then the communication begins. So how does it work? How does the encryption go on in this case? The client and the server both have a pair of keys called public keys as well as private keys. So the client has public key, the server has a public key. The client has a private key, the server has a private key. Now, before the communication happens, as we saw in the previous example of sent a dinosaur to your garden, so there was an arrangement between these two people. So similarly, the client shares the public key with the server. So the server knows what's the client's public key, and same for the other side. So then what happens when the client's server sends a random message? The client then encrypts that message using the private key and sends it to the server, and then the server can decrypt it using the public key. And once the decryption is done, so the real message and the message sent randomly matches. That means the public key was the correct one that the client had. So that means it can be trusted, and that's how the communication begins. Now, how is that done? So what is the mathematics behind this encryption mechanism? Okay, so that is what we are interested in today. So not very complicated, but you have to know a few things here and there, basic arithmetic. So what is the maths behind public key encryption? Most of us do not even realize what happens. We just do a SSH, username @ IP address, and then we provide a key and we can log in, or we provide a username password and log in. But this is for those of you who are curious to know and dive deep to see what cryptography is and what public key cryptography stands for. So let's begin doing this. All right, let's take two prime numbers. Now, why prime numbers? I'll talk about that in the end of this session. So let's take two prime numbers, say P and Q, and you can take any two prime numbers, take smaller ones so that our calculation is simple, because this is just a exercise where we want to learn how it is working actually. So assume P is equal to 7 and q is equal to, say, 13. Alright, so next what we'll do is we'll multiply p and q. So multiplying p and q will lead to p into q equal to 7 multiplied by 13, and say the result is n. So say n is equal to p into q, so n is equal to 7 into 13, which means n is equal to 91. Alright, so we have our first figure that we have to remember. You'll understand in a while why. So we are taking two prime numbers, multiplying them, and the result is 91, and we store the result as n. Alright, so that is the first step. And then what happens is that we calculate something called Euler's totient function. Let me quickly tell you what it is. In number theory, Euler's totient function counts the positive integers up to a given integer n that are relatively prime to n. So you will see, like, the definition sounds a bit cryptic, but once I calculate it, you'll see it's pretty simple. So let's compute Euler's totient function of n. So how is that calculated? Those of you who are interested in maths and want to know more about Euler's totient function, there is a very good video about it in the cryptography section of Khan Academy. It's a free video, so you can just look it up on Google, and you can watch this. Well, let me begin. So phi of n, the Euler function is denoted by phi, is p minus 1 multiplied by q minus 1. So phi of n, or the Euler totient function, is phi of 91 in our case, because n was 91. P was 7, so 7 minus 1 multiplied by q was 13 minus 1. So it will be 6 multiplied by 12. So phi of 91 is equal to 6 into 12, which would be 72. So phi 91 equal to 72. Alright, so we got another number of significance. So I'll tell you what it is and how it will be used in our public key scheme of things. Alright, so next what we do is pick a random number called E. That number should fulfill some conditions, that is, E should be such that it is a coprime. Now those of you again want to understand what coprime is. A coprime number is a set of numbers or integers which have only 1 as their common factor. That is, the highest common factor, or HCF, will be 1. So coprime numbers are also known as relatively prime or mutually prime numbers. It is important that there should be two numbers in order to form coprimes, of course, because you cannot just have one. Well, apart from that, in our case, we have to find a coprime phi n equal to 72, and some other conditions should be fulfilled. That is, 1 is less than e, the random number e, which is less than the Euler totient function, that is 72. So we have to take any number which is lying between 1 and 72. So it can be anything, but the only thing is it should be a coprime to 72. So what is that number which is coprime to 72? We can take any number, like there are multiple, so say one such number can be say 23. So assume E equals 23. Alright, so these calculations go on behind the scenes when you do a SSH login. Well, so now we got pretty much some of the magic numbers, E being one of them. And now let's again compute another number called D. Now D will be the modular multiplicative inverse of E, that is mod phi n. And this E will be used for encryption and D will be used for decryption. So now let's start computing the number D. So before we go on to calculate D, we have to understand what modulus function is, because as I said, D is the modular multiplicative inverse. So we need to understand what modular function is and what is a multiplicative inverse, and then only we can find the modular multiplicative inverse of E. So what is a modulus function? A modulus function is a function which gives the absolute value of a number or a variable. It produces the magnitude of the number of variables. It is also termed as an absolute value function. The outcome of this function is always positive no matter what input has been given to the function. Let me give you an example. I ask you time, say it is 3 p.m. You tell that it is 3 p.m. But actually it is say 15.00 in the clock, or when it is 4 it is 16. So what do you do when you tell the time? You translate it into a modular function where 12 is something which resets the function. So you count from 12, 1, 2, 3, so 13, 14, 15, so 3 p.m. So that's how we do. Say someone says 23, then we don't say 23, we say 11 p.m. So because we count the modulo after 12. So that is how it works. Well, coming back here, our D value will be the reverse multiplicative inverse of the modulo function. So 23 and into D equal to 1 mod 72, because we are calculating the multiplicative inverse here. So that comes out to be 23 into 47 equals 1 mod 72, which means D is actually 47. Now with this calculation of D, we have completed our all the magic numbers that we'll need for this particular exercise. So now we have public key, that is n equal to 91 and E is 23, that can be used to encrypt. We have a private key, n equals 91 and D equals 47. So that is how public and private keys are calculated. So just by taking in random prime numbers. Now you might be wondering, how does the message encryption work then? So the way to do that is, let's take another example here. Say someone wants to send you a message M, and say the message contains the decimal number 60. Computers normally speak in binary, so that would be the binary equivalent of 60. So we are just using decimal for our understanding and convenience. So let's say m equals 60, 60, and we will use the formulas to encrypt this number 60 and send it over and see how using the public key the encryption is done, and then how using the private key the decryption is done. So that will close the entire story for us and we'll know how it works, and then we'll move on to understand like why prime numbers were taken, and if we can decrypt it, then why can't any other people using computers can decrypt and steal the keys. So we'll talk about that. Well, so m is equal to 60, say, and say I want to encrypt it, so the function c of m is equal to m to the power e mod n. So this will be c60 23 mod 91, that will be c60 will be, sorry, equal to 44 here. Alright, so let me write it down. c60 equal to 44. So here the encrypted number using the public key is 44. So they will send you this number 44. The actual message is 60, but you'll get a number 44. Now it's your turn to decrypt this message using your private key. So we have private key 91, n is equal to 91, d is equal to 47. So we'll use that to decrypt this 44, and the answer we will get should be 60. And if we get 60, that means we were able to encrypt and decrypt it. So let's decrypt the message now. Well, here we have a cipher c is equal to 44. Let me write it down. And we'll do this using the private key, of course. N comma d, where n was 91 and d was 47, of course. Now c equal to 44, so m of c equal to c to the power d mod n, and that would mean m of 44 equal to 44 to the power 47 mod 91, and m44 equal to 60 in that case. So m is 60. So we have the secret here. So 60 is the original message. So that is how the decryption is done. Alright, so that is how we do the encryption, and we have done the decryption as well. Now you might be wondering why people use prime numbers here. The reason is prime numbers are complex, like to solve them it takes time, and when SSH works it uses large numbers, very large numbers. It doesn't use numbers like we chose p and q, p is equal to 7 and q is 13, not like that. Big numbers, very large numbers. so that computing it takes a long time and almost impossible for modern computers to do that. Maybe with the adoption of quantum computing, this problem will be completely changed, and maybe these algorithms will become irrelevant then, but that is how it is now. So for now it is safe. And why do we use prime numbers? As I said, calculating large primes is complex, so you can see for yourself. Let me open a Python terminal. So I'm in Python. So if I write something like this, set 91 by I for I in range 1 to 91, if I, and then I'll find this modulus function, then I get the answer very quickly for 13 and 7, those two numbers, P and Q. But if I take a very large number, and let's see how long my laptop takes to calculate this one. So what we are doing is just factorization, but that will give you an idea what happens when we take large prime numbers. So I'm replacing the 91 to this large number, but that was too large for Python to convert to C long. So let me reduce it a bit. This should be fine, and let's hit enter. So it starts calculating it, but you will see it takes a long time, not as quick as it was before when we used 91, 13 and 7. So it's still calculating, nothing happens. We will have to wait forever. I'm cancelling this. Hit a Control D and exited out of it. And so, my friends, that is how encryption and decryption works behind the scenes for SSH, and that is the mathematics behind it. Thank you.